All right, let's talk about the example problem of a swimming pool siphon. Normally this time of year, whenever I teach this course, it's normally in the It's normally either in the fall or the spring. In this case, the spring semester. It's about the time when I'm going to start draining my swimming pool and get ready to restart it for the year. Loud pop here, sorry. So, example. Now, if you've never set a siphon for a swimming pool before, to drain it, or it could be draining anything, right? The idea of a siphon is, let's say you've got some reservoir. In this case, it's going to be a swimming pool. Right, and you put a hose of some kind into that reservoir. Okay. Now this hose then, for me, what I do is I just take it, I fill it up. You fill it up with water. In this case, if you're draining your swimming pool, you fill it up with water. Some people will just take the entire hose, put it all in the pool, and get the whole thing filled up. I normally just hook it up to my faucet or my outside hydrant, start putting water into the pool, turn the hydrant off, unscrew the end of the hose from the hydrant, and then take that end downhill. So what happens is I fill the entire hose full of water, right? And it's going to have some coils down here. Right, some coils on this hose. And then down the hill a little ways, you have the outlet of the hose. Awesome drawing skills here. Okay? So, simple rubber garden hose. Nothing fancy, nothing too terribly expensive. And what happens is you'll have flow, water flow coming out of that garden hose. Well, as the molecules leave the garden hose, they get replaced by molecules from in here, and they pull more molecules through, and more molecules get pulled through. What replaces them? Well, the only thing left to replace them is water out of the pool. So if this entire hose is completely filled up, and you put one end of the hose lower than the elevation of the pool, the surface of the pool, you set up a hydraulic potential here. You set up some elevation head. Right? Let's say I set the hose about 5 foot downhill somewhere. I've got 5 foot of potential energy between the surface of the pool and the outlet of the hose that I can use then to push fluid into the hose down the hill, even though it comes up and over the side of the pool, and then down the hill and flows out. Because again, why does it go up? Well, because there's nothing, you generate a vacuum otherwise, and the vacuum sucks more fluid in there, right? As fluid leaves, it's going to generate a vacuum. Well, the fluid down here is leaving the hose, so more has to go in. So some things we know here. What's our given information? Well, I've got rubber hose. I've got a diameter here of 3/4 inch rubber hose, give or take. It's a nice, large garden hose. And it's water, we'll say, I don't know, 40 degrees Fahrenheit. The length of the hose is 50 feet. And again, let's estimate, I didn't go out and put a surveyor's tape or anything like that on it, but let's estimate an elevation drop of 5 feet between the surface of the pool. Let's say it's probably 2 feet up on the surface of the pool, and it's probably 3 foot down the hill, right, from the bottom of the pool. So it's probably a total drop of 5 feet. Let's see, I don't know if we need anything else here to estimate the flow rate. Again, if you're not in my course, maybe you use Q to represent flow rate. In our text, we use V with a dot above it, volume with a dot above it. That's volumetric flow rate for us. So we want to estimate this volumetric flow rate. Well, let's look at the energy associated with this, because that's really all that's driving this, is the potential energy between this surface and the outlet down here. So I've got an elevation here. Let's say V1 is approximately 0, right? Let's make some assumptions here. Right, we're going to assume P1 and P2 are both 1 atmosphere. I call 1 the surface of the fluid here and the surface of the pool, and 2 the outlet. Let's assume V1 is negligible. Right? V2 is going to be much larger. The speed here is going to be much larger than the speed there. Right? That's a given. And so the pressures go away. There's no pump. So really, all I've got is the initial elevation is going to equal the final elevation plus V2 squared over 2. I'm going to assume alpha to be approximately 1, the kinetic energy correction factor. And then I'm going to have a head loss here also. So it's V squared over 2G. Let's work in head form, because everything's based off of this potential head here. So let's just work in head form. Okay, so V2 squared over 2G plus the head loss coming out. And I think that's, I'm just going to set my tablet aside here and give me some more room. It's a little awkward to work around it. Alright, so this is page 2 for this set of videos, this lecture. Okay, so how do we find this head loss? Well, that head loss is going to be, I'm going to have both major and minor losses. I've got a 50-foot section of hose here, FL over D, V squared over 2G. And I'm going to have a minor loss. I've got a bunch of bends. So let's see if we can approximate a minor loss for each one of these bends. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 looks like. 9, I guess. I've got 9. I've got 1, 2, 3, 4 coils. So there's 2 bends on each coil. So 9 bends. And I've got a pipe inlet there we probably want to account for. And let's see what else. So it's V, sum of KL, V squared over 2G. And this is going to be V2. This is going to be the speed, because V2 is going to be the same. It's going to be the same speed in the pipe as it is at the exit. Okay. So, and if we say, let's say Z2 is 0. If I say Z2 is 0, so this one goes away, then I'm just left with Z1 is equal to V2 squared over 2G plus FL over D V2 squared over 2G plus sum KL V2 squared over 2G. Notice I can factor all of those. I've got 1 times V squared over 2G here. I've got FLD over 2G, and I've got sum KL over 2G. So I can factor out of all of them a common factor. Right? Well, every one of these has got V2 squared in it, so I can just factor that out. V2 squared times, let's say 1 over 2G plus FLD 1 over 2G, and I can factor that 1 over 2G out if you like to. I'm going to leave it in there. You do your algebra however you like. I'm going to leave it in there for right now. I think that's going to be easier. I don't know. Maybe it's not any easier. Now, why would I do that? Well, I'm trying to find V dot. V dot is going to be a function of the speed. So since I don't know V dot, I don't know speed. But I know everything else here where I can look up sum KL. I know everything else here except for the Darcy friction factor. I'm going to have to guess and check that because I don't know the speed or flow rate. And that's okay, we can do that. Let's set everything else up so we can do that easily. Okay, so what else do we need to know? Well, we need to know, I don't know this V2, but I don't think I need to know V2. I think I can solve around it, or at least that's what I'm going to do. I'm going to say V dot is equal to A2 V2, and this is pi D, you can say D2 or just D squared over 4, either way works, times V2, which tells me that V2 is going to equal 4 times this volumetric flow rate I'm looking for, divided by pi, divided by D squared. I'm going to drop the 2. It's the same diameter throughout, so I'm just going to drop the 2 right now. Now, this is good, this is going to be helpful, but I also need to know what is V2 squared. So if I square this thing, V2 squared is going to be 16 V dot squared over pi squared D to the 4th. So I've got 2 expressions, and this is V2 squared. Right? So if I square this side, I got to square that side. So V2 and V2 squared. I'm going to need both of these expressions because I don't need V2. I'm just going to solve around it algebraically. That's how I like to do these problems. Okay, this is page 2. I'm going to set this to the side here. All right, now what? Well, as I said, we got to find V2. V2 gives us V dot. To find V2, I need to know F, because I know everything else in this expression except for F. Now the problem becomes F, assuming, well, F is going to be a function. That Darcy friction factor is a function of the Reynolds number and the roughness, what we call the relative roughness of the pipe. The fact we know it's a rubber hose, we can go look up an epsilon value. We know diameter, so this one can be found. The problem is the Reynolds number. The Reynolds number, of course, is rho v d over mu. D for circular pipes is just diameter. And again, I don't know V, so, but I don't necessarily have to know V. I'm just looking for V dots. Okay, so I'm going to solve around that V there. I'm just going to plug in here. This is going to be 4 V dot rho, or 4 rho V dot. Now, I'm going to plug in, so again, I'm plugging this quantity in here for V. So when I do that, I'm going to get over mu pi and 1 diameter. And so over here it's over D squared, and I've got 1 diameter in the numerator, so I end up with just, basically I've got 2 diameters in the denominator and 1 diameter in the numerator, so I end up with just 1 in the denominator. So this would be the Reynolds number as a function of the volumetric flow rate instead of the speed. Okay, does that help us? Well, kind of. Here's the truth. Anytime you don't know the diameter or you don't know the flow rate, you're going to have to guess the unknown quantity. So we're going to have to guess the flow rate here. If I guess the flow rate, you can see now, because I know the diameter, if I guess the flow rate, that's going to give me the Reynolds number. Using the Reynolds number and the relative roughness, I can then find the Darcy friction factor. Using the Darcy friction factor back over here, then my only unknown, and I can plug this in here and put this in terms of V dot. My only unknown then becomes, if I know the Darcy friction factor, my only unknown then becomes the V dot. So the Darcy friction factor plus the initial elevation is going to give me a better guess at the volumetric flow rate. And then I'm going to repeat that set over and over again until I keep getting the same volumetric flow rate. And there's my alarm. That's actually a good place to stop. We're going to stop right there. You're going to hear a pop here.